I'm going to talk about the AC winding resistance for the magnetics of a DC to DC converter. It's a very advanced topic. Most people don't get involved in this. It usually takes about 10 years of training in power electronics before you even start to think about it. But unfortunately, the winding resistance changing with frequency affects all of us from day one. So it'd be nice if we had a tool that can help us predict that, and we do with RidleyWorks. So let's get started.
Specifications to start your design.
Here's our input voltage of 360 to 400 volts. That's what you might see with an output of a power factor correction circuit, and it's 12 volts, 20 amps on the output with a frequency of 100 kilohertz. So let's look at the waveforms of this converter. Start with the primary winding waveform. So here we can see startup, current limit, and then it's coming into regulation. We'll continue that simulation and zoom in a little bit. And we can see our primary switch waveform and also the primary winding waveform, which has a strong AC component both at 100 kilohertz and of course the harmonics thereof that is going to increase the losses in the winding. Now let's go look at the winding design in the transformer. So we click on the little transformer icon here.
Transformer Designer.
And a new feature of RidleyWorks is the Ridley IQ, which applies intelligence to designing the magnetics for you. It chooses the core, finds the primary winding structure, the secondary winding structure, automates the whole thing to make your design much easier. We'll talk about that more in subsequent videos. Let's go look at our primary right now. So the primary is wound with 27 turns of wire, 27 gauge wire in 4 layers, high voltage input. And we can see if we just do DC calculations, there's only about 0.76 watts of loss. But if you do AC winding calculations, it's 2 watts of loss. So it's about 3 times as much. So we cannot ignore this effect. It's a big effect. Now let's go look at the actual graph of AC winding resistance. And here it is. And the way we get this graph is by asking
Calculating AC resistance for transformer primary.
So it's going to sweep the AC resistance versus frequency.
10 kilohertz.
And you can't see this on your screen, but if you had RidleyWorks, you would see the value of resistance climbing from 0.5
100
ohm.
kilohertz.
Now it's at 2 point something ohms. Now it's at 10 ohms. So it climbs very rapidly. And then when it's done,
1 megahertz.
Sweeping up to 10 megahertz. Just a moment.
10 megahertz.
So a tremendous
Solution
amount of calculation is done during that time. Again, this takes a huge amount of experience to understand what's going on here. But what we do with that model, we actually build a circuit model which will give you the same AC resistance curve. So this little circuit model will show the resistance climbing from 0.6 ohms or so here, and it's 2 point something ohms at 100 kilohertz. It's 10 ohms at 300 kilohertz. There'll be a lot of third harmonic in there, so that will definitely affect the performance of the converter. What should we do with this model? Well, we throw it out to our good friend LTspice.
Creating LTspice schematics.
There you go, we're done with that. Now we go into LTspice. We open up that file that's created. You see, there's no work in doing that for you. You just click a button and we've got the LTspice schematic. This is going to simulate our converter closed loop with proximity loss in the primary winding. So here's the AC resistance of the primary for a 4-layer winding in this case. Let's run a simulation. Now let's look at that same waveform in the primary that we did in RidleyWorks. Here is the primary switch current, and you can see it coming into steady state here. So let's stop that. Zoom in a little bit on that. And we can see, zoom in a little bit more. So we can see it's a more complex waveform than RidleyWorks because this actually includes the magnetizing inductance, which we don't do in the more simplified, high-speed simulation. Now let's look at our losses. So here is the loss in the primary resistance. This is just the DC resistance, which would tell us the same number that RidleyWorks told us. It's about 0.77 watts. And then the loss in the AC resistance, we click on that other element, it pulls out the AC resistance loss. And now we see there's actually 3.5 watts. RidleyWorks was predicting only 2 watts of loss in the winding, and the losses are higher in LTspice because it's using all of the harmonics in the calculation, and the resistance is climbing rapidly with frequency. So now we can see we've got almost 4 times the loss that we expected, and now you can redesign your transformer to take care of that if you know how to do that. RidleyIQ will do that automatically. It will find the lower loss case, and there's many other approaches you can take to improve the winding resistance. We'll do that in a subsequent video here on RidleyWorks. So there you go. So that's the calculation of AC resistance. You can start incorporating that into your designs right away. You don't need to understand the depths of the topic. It's a topic that's been around since the 1930s. People were very worried about AC resistances even back then. And now you have this convenient tool for you to very, very rapidly design, simulate, and then redesign your transformer to lower your losses. So thanks for watching. Remember, you can see lots of videos on the operation of RidleyWorks, and of course lots of other videos on general design of DC to converters in our website, ridleyengineering.com, and just go to the Design Center. Thank you.